Okay, so I would like to thank organizers for this opportunity. So I'll be talking about these terms in title, Euler characteristic. But so basically, this will be product of sizes of certain cohomology groups, alternating products, as in most of the mathematics we see, but as it comes in Iwasawa theory. So let me fix an odd prime P. So I'll begin by fixing few notations. So first is I fix an odd prime P, and let G be a p-adic analytic group. Maybe I take be a compact p-adic analytic group. And further, let me write in the beginning, fix this subgroup. So let H subgroup of G closed such that I define this gamma as G mod H, which is isomorphic to ZP. So this is my assumption. So I'll be considering these kind of p-adically groups, basically p-adic analytic groups. And so I will be considering these groups and also Iwasawa algebras over these groups. So let me write in the beginning for a general profinite group. So let for a profinite group G put. So these algebras has already appeared in several talks before, including the first talk today. This is the inverse limit of ZP G mod U. So here U varies over open, normal, subgroups. So we have this completed group ring. And so recall this theorem, I mean, this is a fact. This is now standard fact. This is due to Kumar, also maybe Lizards, that this has finite global dimension. So that is the supremum of left and right projective, if supremum of projective dimension of left and right modules is some finite integer. So that's the property. So basically, it was discussed in the first talk today. Basically, what happens is that if I have a R, say for example, complete Noetherian local ring, then maybe in the case we are looking ZP. So you have this ZP. So this it was proved by Brumer that global dimension of this thing is equals to 1 plus D, where D is the dimension of G as a p-adic analytic manifold, and for a p-adic analytic manifold, p-adic analytic Lie group. Okay, so this is one assumption I haven't put here. This if G has no element of order P, so that we need, otherwise it's anyway fails. So this will be also part of our assumptions. We shall always consider, so this is an assumption that G has no element of, no non-trivial element of order P. Yeah. So that's one assumption. This is so that this has finite global dimension. Then we consider this definition. So it says that, so now let M be a finitely generated lambda G module. Then we say, so whenever I consider a module, I will be considering left modules. unless I say it. So we say the Euler characteristic of the G characteristic of M exists if Hi G comma M is finite for all I and Hij, the homology groups, vanishes for large I. Okay, and if the G Euler characteristic of M exists, then we define it. It as chi of G comma M. This is product of sizes of H lower I, G comma M, and then you take this alternating product. Okay, and that's the Euler characteristic. That's what that's the object of study for this talk. Let me fix few notations. So I mean, if for any abelian group M, put M bracket P, the P primary subgroup of it. So union of M P to the power N and obviously N P to the power N is M belongs to M such that P to the power Nm is 0. Okay, so then let me straight away go to an example, a concrete example. Which examples, the kind of examples which I am interested in. So now let E be an elliptic curve defined over Q, the field of rational numbers. Assume E has good and ordinary reduction at P. So these terms have appeared several times in several talks before. And also, so assume that further, so LE of 1 is not equal to 0. So this is, so here LE S is the Hasse-Weil L function of E over Q. So suppose that the value of E at 1 is non-zero, then we have, so not just the Euler characteristic of, so I'll say what is this gamma of this Selmer group is the same which was defined in the first talk today by Professor Sujatha. This over U cyclotomic, we take the Pontryagin dual. This is equals to, there is formula for this, up to P part. This is same as, you take L, E at 1, you divide it by its smallest non-negative and non-zero smallest period, basically the period which comes in BHD formula. And then you take the size of E, look at the reduced curve of E at the prime P, and or maybe you can write it Z mod P, the points of E over Z mod P, and it's square. So this is up to P, so this is anyway power of P, this quantity, if it exists. This quantity may not be a power of P, but this just compares the P part of both of them. This in general, I mean, of course, in algebraic integer, you know. So this is the formula, and this is the simplest case of. So this is a consequence of. Okay, let me state this is not in general. So this is a consequence of. I mean, so you have, maybe I should say this way. Then BST plus control theorem implies this. So this is actually this is how Euler characteristics appear in Iwasawa theory. So these examples I wanted to. This also is a consequence of main conjecture, Iwasawa main conjecture. Whenever you know it, of course, then there is a question of which period you take. That's again, if the residual representation is irreducible, then it differs by in their own period by a p-adic unit. Sorry? Okay. So the gamma is Galois group of Q cycloatomic over Q. And what is Q cycloatomic? Let me just write down here. So you have Q and you have Q mu p infinity. So you attach all p power roots of unity. And then inside this we have an extension such that this Galois group is isomorphic to Z. Okay, so gamma is the Galois group of Q cycloatomic over Q. Okay, the Selmer group on the gamma acts on Selmer group that was explained in the first talk today. So again here the assumption that he has good and ordinary reduction is important. Otherwise the formula is not true. Even all characteristic may not exist. Okay, so there are other examples which were again some of these extensions appeared in the first talk today. So you take maybe k infinity to be Q and mu p infinity, and in that you attach some integer you take. So some minimal conditions you have to put, and then you attach all the p power roots of that and take the union of over L. Okay, so if you choose M appropriately, then this is a Galois group of. So you have to choose, let's say choose M such that M to the power 1 by P does not belongs to cycloatomic. Sorry, Q mu P infinity. Then this is a Galois group of K infinity over K. Q is a p-adic analytic group of dimension 2. Finitely ramified in the sense that there are finitely many primes of Q which ramifies here, prime divisors of M and the prime P. It's totally ramified at P. So then again there is a formula. This is due to again if you apply BSD plus the control theorem again, in this case control theorem is proved by Hachimura and Veniaco. In fact, they gave the Euler characteristic formula itself. So that again tells you, if you take this, call it G, then G of Selmer group P infinity, you take EK infinity. You have to take contract and dual of this. If you want to consider Euler characteristic the way I have defined using homology group, you can also consider define it using group cohomology. Then you don't need to take contract and dual. So in this case, this actually turned out to be Euler characteristic of gamma and Selmer group over. So for this part, you don't need BSD. If you write down the formula for this, then you need BSD. And then E, again, this is Q cycloatomic and contract and dual. And then there are some local Euler factors. So V belongs to some primes, set of primes, which this sigma naught is a set of primes divisors of M, not all divisors, but some of them I don't want to describe. And then you have to take a local L factor at that, E, comma 1. Okay? Which one? Yes, because this LE of 1 is non-zero, so actually you know that Selmer group itself is finite. Rank is 0 and size finite. And then this again, I mean, that's why full force of BHD is needed. Otherwise, what you get is, again, you can write down the formula. In that case, here some size of Selmer group comes, which is in fact, if you know the rank is 0, then size of SA comes, and then few other terms comes. Again, here, so here, this is gamma is again, so I have K infinity, Q cyclotomic, and Q, and the Gala group is, this is gamma, this is G. So yeah, this is the formula. These are some local L factors appear here, which depend, this set of primes depend on this integer M. Okay. So these are the two special cases of examples which I wanted to discuss. There are now, I mean, there are many more cases. For example, in the morning talk, it was discussed the case of, I mean, if you consider the p-adically extension, a p-adic analytic extension by attaching the p-division points of elliptic curve, p-torsion points of elliptic curves, then again there is a formula by Coates and Haugen, and then there are formula by Sujatha, Coates, and Snyder for different kind of extensions. Okay, so to write down this, you don't need BSD. If you want to substitute this, then it's needed. So these are the examples which appear in Iwasawa theory. Okay, so let me fix some notation. So again, let M be a finitely generated lambda G modules. Again, for me, G is a compact p-adic analytic group which has no element of, which has no p-torsion. So then I consider this and let rho from gamma to, so gamma is a quotient of G in this case. Let's take a character ZP and then put M. So I define this M rho, this is notation, which M tensor ZP over rho with diagonal action of G. So note that this gamma acts on rank 1 GP module via rho, and then because this is a quotient of G, so G also acts. So this is a G module, this is a G module. So we get action of G on this new, so we get a new lambda G module, and it is again finitely generated. So, I mean, this is a fact, or rather well known. We can call it twisted lemma. This is stated by, I mean, easy consequence of commutative algebra also. This has been stated and used extensively by Greenberg and in some of their articles, which says that if M is a finitely generated torsion lambda gamma module, then there exists continuous. So again, I mean, considering I'm not saying every time a continuous module or continuous character, but those things are there in the background. Okay, so and then there is a continuous character rho from gamma to ZP star such that chi of gamma to p to the power n m rho exists for all n. Okay, so not just gamma, but gamma Euler characteristic, but all its subgroups Euler characteristic also exist. So you can find one such row independent of this n. In fact, exist for all n. This n. Okay, so this is a little lemma which also they have used to. So if you want to prove the functional equation, for example, for say the characteristic ideal, then this is, for example, this is, in fact, they need H naught finite, but there are many more places this they have used. Okay. Okay, so now let me just mention this, this standard thing which now, because I have talked about this lemma, so an example where you can apply, and this is due to Kato, that again for us E has good, in fact you don't need good, so let E has ordinary reduction at P, then Selmer group E infinity, EQ cycloatomic, or in fact more generally an abelian extension, dual is a torsion lambda gamma module. Here gamma is again Galois group of. Okay, so this example, standard example where you can apply this lemma. So now let's consider some non-commutative situations. So now let K infinity over Q be a p-adic analytic, or p-adic Lie extension also we can call, analytic extension. That is a Galois group of this is a compact p-adic Lie group. Okay, and further suppose that K infinity over Q is finitely ramified. That means that there are finitely many primes of Q which are ramified in K infinity. Then, and further ramified. Now, if the Iwasawa mu invariant of this Selmer group, which was defined in the first talk today, of Selmer P infinity E over Q cycloatomic, or we are considering here okay. This is nothing specific about Q. You can also consider any number field. This is 0 and G is also rho P. Then Selmer group E over K infinity dual is a finitely generated lambda H module. Okay, so again our assumption this E has again we continue to assume E has good and ordinary reduction at primes dividing P, and okay, I should also say here, when I say mu invariant 0, of course I need to also know that whether over cycloatomic extension this thing is torsion or not. So 0, comma, and Selmer E which is always expected to be true. But, and okay, so this is a finitely generated ZPH module. So you notice, you remember this? I had this. This is inside lambda G. So if I consider a lambda G module, that's also a lambda H module. So Selmer groups are lambda H modules. So I am now viewing it as a modulus over this algebra. So this is a finitely generated lambda H module. This follows from control. This is a well-known result. It again appears in many of the articles by even, for example, Veniakov, Hachimura and Veniakov, and also quotes Sujatha and Snyder. And after that, many other places in different cases. Okay, so this motivates us to define this category. So let us define. So let M H of G be the category of finitely generated lambda G modules such that M mod M bracket P, which was defined earlier, is a finitely generated lambda H module. Okay, so let me stick to this. Let me here also mention this conjecture. Again, this is by Coates, Fukaya, this says that if E has good and ordinary reduction over primes dividing P and G equals to Galois group of, so maybe I should say comma here, K infinity over K is pro P, p-adic analytic p-adic Lie without P torsion and K cyclotomic is contained in K infinity. They call such kind of extension admissible extension. Then Selmer P infinity E K infinity dual is in MHFG. So this is a conjecture. This conjecture now, because of that remark, that theorem which I had stated, it's true when the Iwasawa mean variant for the Selmer group over cyclotomic extension is 0 because of the control theorem there. But in general, it's not known. If the mean variant is positive, then we don't know. There is not even a single example where mean variant is positive over cyclotomic extension, and this conjecture is true for the Selmer group. Okay, but there are, of course, large number of examples where mean variant itself is 0, and so this conjecture is true. Okay, so our main theorem now let me state. Okay, so the theorem state is let M be a finitely generated lambda G module which is in M H of G. So I assume a module which satisfies this property. Then there exists a row, again continuous, from gamma to ZP star, such that this U M rho, this exist for all open normal subgroup U contained in G. So you can see that it's now a direct generalization of the theorem of Greenberg or Perrin-Rieux, which he had stated. But for a general p-adic group, a p-adic analytic group, it satisfies this property that it has a quotient which is isomorphic to ZP. In fact, we proved something stronger. In fact, we saw that there exists a countable set Sm of characters from gamma to ZP star such that if rho does not belong to Sm, then chi of U. So this is again for all open subgroups. It's just like there we had all open subgroup gamma to the power p to the power n. Exist. Okay, so this is for all U contained in G open normal. Okay, so this is the theorem in general. Okay, so let me. So of course our motive. So I mean all the examples of Selmer groups which we have considered, there was no twist there. But then if you consider modular forms and different critical points, then we want to study the Euler characteristic at different cyclotomic twists, then immediately these kind of Euler characteristic you come across. So here I have assumed this M is in MH of G, but I mean there is a lemma or by Sudhanshu. It says that if M equals to M of P, then so basically if M is P primary, then for any so if take any p-adic analytic group without an element of order P, some finite dimension, then this M exists. So if I have a P primary, then Euler characteristic always exists. There is nothing. So you remember we had this M, and then M mod MP primary, and then 0, and then here you had P primary. So we are assuming, because we are assuming that this is in MH of G, so that means this is a finitely generated ZPH module. This Euler characteristic always exists. So if you want to prove this kind of theorem, then it's enough to prove modules which are ZP gamma module, but also finitely generated ZPH module. So it problem reduces to that, because once the Euler characteristic of this exists, then Euler characteristic of this exists if and only if Euler characteristic of this exists. Same happens with if we twist it. Okay. So one of the key lemma, I should say, or result maybe I should say. This is due to one of our author, and Uchiai, and then Paddy. So what they show is that if M is in maybe I should say M is in MH of G, then there exists a rho gamma to ZP star such that this is M rho U, which is actually H naught of U comma M rho. This exists for all U contained in G open normal. Okay, so they show for H naught. But we want to do it for all HI. That's what we want to do. But let me here point out. Sorry. Yeah. This is for all. Yeah. Thank you. Okay. So you see H0 is finite, that we know. The question is what about Hi? So there is a theorem by, maybe theorem. This is by Wortsley. This is by Wortsley, SLY. That they define what are called finite by nilpotent groups. So if I won't define it, G is what is called finite by nilpotent, then H0 G M, this is for any, again, p-adically group without an element of order P. So if this is, this finite implies exist. Okay? I mean, specifically if, like for example, if we take, if G is a commutative, and then because of this, then H0 Gm, so this is because of this theorem, H0 G finite implies chi G exist. Okay, so this kind of groups, it's true, but there are examples, but remark. So there are examples. And this is by Haugen, maybe Ballester, Haugen. I think so. There are examples such that H0 of Gm is finite, but chi Gm do not exist. Okay, so something non-trivial is happening. It's not sufficient to. In fact, this for commutative case it also follows from commutative algebra. It's basically tau naught is for a regular local ring. You have tau naught is 0, so one need to show all tau i's are finite. But for non-commutative, this kind of groups, he has proved it. But there are examples where it fails. So that's where there are a few more remarks. Of course, in the case, so if I have, so also I would like to say that if M is not in MH of G, then there are examples. This is by, Coates, Fukaya, Kato, Sujatha, and Veniakov in their paper, that chi Gm rho do not exist for any rho. Okay, so all these assumptions are needed here, otherwise it fails. And also the assumption that G has no element of order P is essential. Otherwise, do not have finite, global dimension. Other characteristic will not exist for many, may not exist for many examples. So all these assumptions are needed. So let me now briefly sketch the proof. So we need to somehow use the fact that you can find, in fact, you can find many rows as that H0 is finite. We need to use that. So one of the, observation, a basic observation, note that if there exists maybe any W maybe closed such that chi of W comma M exists or M row exists, for any module this is true, then chi of G M also exists. Okay. So this is, this follows from Hochschild cell. So we basically try to find, given any such a group, we need to find some smaller subgroup. In fact, we find a finite index subgroup such that all the characteristics exist. No, this will work if you have any close, but if you have a profinite group, if you take a finite index, then it's going to be complement is again open, so that subgroup is anyway closed. So of course, if you want to, we will find basically a open subgroup, but also true for any in general. This is also true for. Okay. So here, so we shall try to find some open subgroup here. In fact, a finite index open subgroup. Now, maybe I should say here, of course, also normal you need to assume. Okay. So key technical lemma is this. Maybe key lemma. Technical one, which somehow uses both homological algebra and topology coming from this completed group algebras. So this is this, that if M is a finitely generated lambda G module which is also a finitely generated lambda H module, then there exists an open normal subgroup, let me call it G0 of G with H is contained in G0 and resolution M 0, N1, and K such that so Nk by finitely generated lambda G modules, G0 modules, such that each Ni is a finitely generated free lambda H module. Okay, so we are not able to do it for G itself, but we can find a smaller open normal subgroup G0. That's where little of topology comes. We have to somehow use a sequence of, basically a neighborhood of 0 of this module M, and we have to go shrink it a little bit. So we can find such a resolution of lambda G0 modules. But nice thing what we get is that each of these is a free finitely generated free lambda H module. Okay, here H is contained in G0. That's how we find G0. Once we have this, then so actually what we do is we successively create here. We first find a surjection, then keep doing it, and then use that it has finite projective dimension to stop somewhere. Okay? Which one? Yeah, each of them is these are lambda G0 modules, but I mean further they satisfy that they are free, they are lambda G0 modules, but they satisfy that they are free, finitely generated free lambda H module also. Okay, so once we have this, so now what we are reduced to is, let's show that Euler characteristic of each of these Ni exist, I mean for some twist. So we have to find a twist rho which is common for each of these Ni. So we need to basically find rho such that chi of u Ni rho exist for all I. Okay, so that's what we need to do. Okay, because if each of these Ni, for each of these Ni Euler characteristic exist, then it will exist for M. Okay, so how do we do it? So what basically, let me just briefly say what basically we do. So we have now a free, this is a lambda G0 model, but this is also isomorphic to this to the power d for some d. Okay, and notice that we have this G and this surjects onto gamma, which is generated by this small gamma, it's a topologically cyclic. So what we basically do is, we take an element from G, whose image is this. So basically, take a lift of this inside G. Again, let's call this maybe gamma tilde. And this acts on this module. So this induces a map here. So basically, we get a matrix. I mean, by applying on standard, this is a free module, so we have standard basis. So we get a matrix out of it. So basically, what we show is that. So let's call this matrix. So let gamma acts by some matrix A, belongs to GL, whatever D of lambda H. Okay, so then basically what we do is we find we basically give a, so we give a structure of Ni as in terms of generators and relations, in the sense that you can show this Ni as in the sense that this Ni is isomorphic to lambda G and to the power D modulo lambda G to the power D, and here we have this gamma tilde minus some gamma tilde identity matrix minus A, this kind of expression we find out. Okay, so you notice that from right side we multiply it. Okay, so that's how this becomes a left module now. So this isomorphism, we have such an isomorphism. Okay. So once we have this, then we have that implies that it has a projective dimension 1. So that means we have you have to use that. Of course, you have to use that. This so that injective, and then so we get a map here. Somehow construct a map such that basically we show that using this structure theorem, we show that it has projective dimension 1, And then you apply H naught. So we have basically H naught is, going modulo U, so you apply U for any, so U open normal of G naught, apply U, and U, and then here we have H1 of U, and then N. And then we get 0 here, because these are free, lambda G modules. So now you see, once you apply U, then this has ZP rank of, so they have, ZP rank of middle two terms are same. Okay, so this implies H naught of U of N is finite if and only if H1 of U of M is finite. Okay, so this is true for these are free at pH modules. That's why we are able to give such a structure, and we are able to show that has projective dimension less than equals to 1. And so that means Euler characteristic of this N exists, but for that, so this is exists if H naught is finite. So then we need to find some rho such that H naught is finite, and that's where we use the theorem of Jha, Jabradi, and OGI. So you have to twist it, and then we apply theorem. And there are uncountably many such rows, so basically we take a common among all these. So there are uncountably many rows for which Euler characteristic of each of these Ni exists, and then we take intersection of them. From there we get such a row. So that's how the theorem goes. So once the Euler characteristic of each of them exists, then for some row, then you take a common row, and Euler characteristic of this M row also exists. So let me now come back to Selmer groups again. One of the motivation for us, and there are several, but maybe I will tell a couple of them. How much time I have? Okay. So motivation for looking, each Euler characteristic. So recall we had this conjecture. I don't want to write all the conditions, but under some of these conditions, we had this conjecture that this dual is in MH of G. Of course, here K infinity is the, again, CYC, this was H, this whole Gala group is G. This is in MH of G. So what we have shown that one way that if, MH of G, this thing is in MH of G, then there are twists for which the Euler characteristic exists for all open normal subgroups of G. But what about the converse? So one of the question we were interested in, that suppose M of H is finitely generated, M of H is finitely generated torsion lambda gamma module. This is something we satisfy for Selmer groups for when it has good ordinary reduction. Is torsion module. Then if chi u m exist for all u G open normal, then can we say that M is in MH of G? The converse is still remaining, which we would like to look at. And this is one of the questions which we are interested in. One way we have already shown. And another thing is related to another group which appeared in the first talk today, which was the Fine-Selmer group. So I mean, recall let E over K infinity be the Fine-Selmer group. I don't want to recall the definition. It was there in the first talk. Be the Fine-Selmer group of E over K infinity, and the conjecture was that this is pseudo-null lambda G module. Let me mention here that if G is isomorphic to gamma, that is ZP, then pseudo-nullity, I mean M is pseudo-nullity, pseudo-null if and only if Euler characteristic of gamma M is actually 1. It vanishes. It's not true for in general for a p-adically group, but this is again this is true. This is true for finite by nilpotent groups. But I mean, all the examples where this fails are actually the abstract modules and nothing to do with Selmer groups or Fine-Selmer groups. So earlier, I mean, other than the cyclotomic case, even the showing that the Euler characteristic of these modules exist, even if, so let me say here just that if Selmer groups are, say for example, is finite over number field, then in the good ordinary case, you can show that under some assumptions, you can show that Euler characteristic exists. But even if this thing is finite over number field, it is not clear how to show the Euler characteristic of these exist over, even though these are smaller, it's not clear how to show the Euler characteristic of these exist over a general p-adically extension. But now we know that, I mean, under a conjecture which was in the morning, a conjecture A which was called, that we know that there are many twists for which the Euler characteristic of this module exists. So now once we have Euler characteristic exist, and if this thing is pseudo-null, I mean, if and only if all its twists are all pseudo-null, that's almost obvious to see. So now, if we assume this pseudo-nullity conjecture, then it's a question whether Euler characteristic of this vanishes or not. Once it exists, we would like to know what happens. There is not a single arithmetic examples in the sense coming from Selmer group or Fine-Selmer group for which, this property which I told you for pseudo-null module fails. So we would like to know for Fine-Selmer group. So some of these questions are of interest. I would like to stop here.